Hello everyone, I am Zhou Xiangyang from the University of Science and Technology Beijing. Today, I would like to share my research project titled Editable Mesh Animations Modeling Based on Controllable Particles for Real-Time XR. First, I would like to briefly introduce my research motivation. Controlling animations to generate a target object has already been applied in fields like visual effects. Creators desire a convenient model that allows them to generate the desired control animation effects in a single step using a simple model. This is one of our motivations. Additionally, to better expand the application areas, we aim to create a final result that is an editable mesh, which greatly enhances creative freedom. We hope this mesh will improve efficiency in design and allow for interactive editing within virtual environments. There have been many excellent control animation algorithms developed previously. For instance, Zhang first introduced the concept of fluid control in 2015, using density constraints and spring constraints to shape fluid particles into target forms. However, this algorithm suffers from instability in control forces, which can lead to particle splashing, and it requires parameter adjustments for different models, making it difficult to control multiple targets simultaneously. In 2019, Liu proposed a skinning mechanism that allows particles to closely adhere to a template. However, this method can only generate simple model outlines and performs poorly in terms of detail, also failing to create hollow models. In 2020, Xiangyang introduced an animation template for controlling fluids, primarily storing predefined templates for easy use. Yet, this algorithm can only control the generation of simple outlines and is unable to produce complex models while maintaining their stability. Generating editable meshes is also a current research hotspot. In 2024, Tang achieved the generation of a mesh model from a single image and text. However, the information contained in a single image is ultimately limited, resulting in a very rough and non-editable mesh model. Antoine, in 2024, used free Gaussian splotting free EGS to generate an editable mesh, but their method has very high requirements for the dataset. Additionally, the generated mesh cannot adapt well to skeletal mapping, necessitating manual labeling and modifications, which is very time-consuming. Next, I would like to introduce our method. The first step we take is to sample the template model. Previous sampling methods, such as those based on implicit functions, have very low flexibility, while methods using signed distance fields can only sample simple models and do not perform well with complex ones. In contrast, we utilize single-layer blue noise surface smoothing sampling, which allows us to capture every detail of complex models. Moreover, the sampled particles are uniformly distributed, providing a solid foundation for the subsequent control algorithms. Next is the core control algorithm module. First, we sample the model using blue noise sampling to obtain a basic particle model. Then, we use air pressure propagation to ensure that the particles are evenly distributed on the model's surface. To prevent particles from moving off the surface, we need to counteract the forces in the normal direction, allowing them to move along the tangential direction. Next, we apply adaptive weights to each control particle based on the model's feature types. We also impose reverse constraints on the surrounding particle density according to the sampling density, ensuring that the generated model is both fast and uniform. The boundary correction force primarily addresses the external forces acting on the particles, ensuring that they continue to move in the tangential direction. Since the resultant force must be calculated from the start of the algorithm, we update the acceleration accordingly. By keeping the displacement update small at each time step, we can prevent excessive force from causing particles to fly off. Moreover, when the density of controlled particles around the control particle reaches a threshold, we reduce the control range. This approach allows for better filling of undersampled areas, and increases the stability of particles in already stable regions. This not only enhances generation efficiency but also improves robustness. The green module represents the core flowchart of the overall algorithm, while the red module illustrates that our algorithm can stabilize control of the model without relying on any model parameters. Our parameters are only used to set the generation speed. The three different types of models show control particles obtained through various sampling methods, all capable of generating quickly and stably within the same scene. From the algorithms I previously introduced, it is clear that our method can accurately generate target models based on spatial distribution features, even under sparse sampling conditions. We provide enhanced control stability, which reduces issues such as particle splashing and shape distortion, thereby improving the reliability of the modeling process. Next, we demonstrate the generation of a real-time editable mesh model. First, the mesh created by our reconstruction algorithm can be directly mapped to any skeletal rig. Once the skeletal mapping is established, we can easily import motion models to generate animations for the model. Finally, we have applied the editable mesh in various VR and AR scenarios, confirming that our algorithm performs exceptionally well. The methods section has been completed, and now we move on to the experimental section. First, we conducted animation experiments for comparison with some of the most advanced control algorithms. In the architectural model, we observed that our method maintains stable performance even under conditions of undersampling. In the warrior model, we noted more stable and efficient control. Through multi-target experiments, we verified that our algorithm does not require unnecessary parameters to adapt to different model types, allowing it to stably control multiple distinct models simultaneously within the same scene. We also conducted experimental comparisons of the mesh reconstruction algorithm. It is clear that our method exhibits superior accuracy and detail in the models. Other algorithms are unable to generate intricate hollow details, while our algorithm effectively addresses this limitation. This advancement provides a new development pathway for the animation field. So, how do we use this in VR and AR applications? It involves two steps. The first step is to import the already mapped skeletal mesh model directly into the editor, where users can modify the skeletal mapping positions. With the skeleton in place, users can freely edit or insert animations. The second step allows users to edit the skeletal information for each frame of the animation, enabling adjustments based on their specific needs. This is our demonstration of VR and AR applications. Both of these applications can maintain around the 120 fps during the animation generation process. The AR application, while potentially having more resources and features, can still sustain 60 fps during control. Additionally, we have developed various technologies for the AR application, such as an AR recognition smoothing filter to prevent issues like model jitter causing clipping. Furthermore, we enable a multi-scene interaction through multi-target recognition. Currently, our algorithm does have some limitations. For instance, armor and capes cannot be modeled in separate sections for free movement. Additionally, in our pursuit of enabling real-time mesh editing, we had to make some compromises in terms of intermediate precision. In the future, we plan to experiment with more high-resolution models. Based on current results, the performance is quite promising, but we still have some distance to cover before achieving real-time applications. Additionally, we hope to enhance the realism of mesh simulations further. Thank you for listening.